Concrete beam supports the wall, which subjects the beam to the uniform loading shown. The beam itself has cross-sectional dimensions of 12 inches by 26 inches and is made from concrete having a specific weight of 150 pounds per cubic foot. Draw the shear and moment diagrams for the beam and specify the maximum moment in the beam. Neglect the weight of the steel reinforcement in the beam. Alright, to begin, let's first of all convert the wall loading into point loads. So on the right hand side we can have 6,400 pounds, and on the right hand side it's going to be 8,000 pounds. Now let's convert load of the concrete beam, which is going to be 12 inches divided by 12 times 26 inches divided by 12 times 150 pounds per cubic foot equals to, and it is 325 pound per foot. And if anybody doesn't know where this 12 came from, this is coming from the conversion from inches to foot. All right, now that we have that, let's convert the beam into point loads as well. So we can have, in the center, we're going to have 975 pounds, and on the right hand side we're going to have 325 times 8, which is 2600 pounds, and on the left hand side it's going to be 325 times 10, which is 3250 pounds. Adding these together, you're going to have 11,250 pounds, and on the left hand side it's going to be 9,000 pounds. Now that we have all the point loads, we know there's going to be external reaction forces. So we can have, I'm going to name these first of all A and B. So we can have AY and BY. And these forces we still have to calculate. To calculate these values, let's take moment about the point B. When we take moment about the point B, we can have counterclockwise 9,000 pounds. It's going to be 4 feet away. Then we have counterclockwise 975 pounds, and it's 9.5 feet away. Then we have counterclockwise 11,250 pounds, and it's 16 feet away. And finally we have clockwise AY, and it's 21 foot away, all equals to 0. Solving for AY, we get our solution as 10,726.786 pounds. And then to find our AY, we simply have to sum the forces in Y direction. So we're going to have 10,726.786 pounds, negative 11,250 pounds, negative 975 pounds, negative 9,000 pounds, finally positive BY, all equals to 0. Solving for BY, we get our solution as 10,498.214. Alright, now we have all the required forces. We can start drawing our shear and moment diagrams. So we're going to begin with the shear. So our shear begins with EY, which is positive 10, 27, 26. Oh, and by the way, I'm going to round these so they are easier to plot. So we're going to make it 10,726 pardon me, 727. So we're beginning at this point, and then from this point we're going to go down 11,250. We're going to be this distance over the course of 10 feet. So we're going to be coming down to negative 523 with the first order curve. And once we are there, we have to go down again another 975 points, which will take us down to negative 1498. Or what is going to happen is something like this. Pardon me, it's also first order curve. Reason being, we have a distributed load here. This is a distributed load as well for the beam. Alright, now that we have that, let me redraw it because it doesn't really reflect. I know this graph isn't to scale, but it should at least reflect some reality. Alright, so this curve looks a little bit better. Okay, and then from there, we're going to go down another 9,000 to negative 10,498 with the first order curve. And from there, BY is going to push us up 10,498. That will bring us to a 0, cementing our assumption for the graph. Okay, next is our moment again. So the for moment, we're going to begin at 0, and then we have a positive area, so our curve is going to go up till this point, but we don't know what is the value of this point. To find out that, we know that this intersection is occurring in this region, which is our region 1. So first of all, we need to determine our load equation for this area. So our load equation for this area is going to be, our region is negative 11,250. Now our shear is going to be simply the integral of the load, 11,250x, plus the constant. To find the constant, we know our shear is going to be 10,727 when x is 0, therefore a constant, and we plug that constant into our shear. Now we want to find out where our shear is 0. And that location in this case is, pardon me, I made just a tiny mistake. I just realized when I was solving this final part. And you might have already recognized this, that our load equation in here, it's not actually 11,250. That was our point load. Our load equation is something different. And to find that, we know that we have found 325 as our distributed load for the beam, and the wall has 800. So adding those together, this comes up to be 1125, and that's our load. Okay. All right, and now our shear is going to be negative 1125x plus the constant, and the constant in this case is going to be, we know already, which is 1027, 10,727. Reason being, we know x will be 0 at this point when we have this value. So we have that. Anyways, moving forward, we want to know where the shear is 0 in our graph. And solving for x, we get the value of x as 953.5 foot. So this is at 953.5, and now we know this will be the peak of our moment, and we know it's going to be concaving downward. And to find the peak, we simply have to take the area of this triangle here. So it's going to be 10,727 times 0.5 times 9.535, which gives us 140.97, rounding it up, going to be 141. And then for this negative triangular area, it's going to be negative 523 times 10 take away 9.535 times 0.5, and this will bring us downwards 122. So 51141 take away 122, and we are at 51019, and this will be concaving downward. Pardon me, the curve will be concaving upwards here. And then we have this area, which is two areas. So it's going to be, first will be negative 523 times 3, which will give us negative 1569. And then this area is 1498 take away 523, and then times this by 3 times 0.5, and that will give us 1462.5. Adding these together, we get our value as 3031.5. We can round it up, so it's going to be 3032 take away 51019. Going to come down to 47,987. And in this, or at this point, our curve is again concaving upward. But in going downward fashion. And now the final area is going to be negative 1498 times 8, and then this bottom area is going to be 10,498 take away 1498, which is 9,000. So 9,000 times 8 times 0.5. Alright, so let's do first one. So it's going to be 1498 times 8, which is 11,984. Bottom one is 9,000 times 8 times 0.5, which is 36,000. Adding these together, we get our solution as negative 47,984 and 0. So curve is going to come down by concaving upwards.